The effects of global warming are the environmental and social changes caused by human emissions of greenhouse gases. There is a scientific consensus that climate change is occurring and that human activities are the primary driver. Many impacts of climate change have already been observed, including glacier retreat, changes in the timing of seasonal events, and changes in agricultural productivity. Future effects of climate change will vary depending on climate change policies and social development. The two main policies to address climate change are reducing human greenhouse gas emissions and adapting to the impacts of climate change. Geoengineering is another policy option. Near-term climate change policies could significantly affect long-term climate change impacts. Stringent mitigation policies might be able to limit global warming to around 2 degrees Celsius or below, relative to pre-industrial levels. Without mitigation, increased energy demand and extensive use of fossil fuels might lead to global warming of around 4 degrees Celsius. Higher magnitudes of global warming would be more difficult to adapt to, and would increase the risk of negative impacts. Definitions. In this article, climate change means a change in climate that persists over a sustained period of time. The World Meteorological Organization defines this time period as 30 years. Examples of climate change include increases in global surface temperature, changes in rainfall patterns, and changes in the frequency of extreme weather events. Changes in climate may be due to natural causes, e.g., changes in the sun's output, or due to human activities, e.g., changing the composition of the atmosphere. Any human-induced changes in climate will occur against a background of natural climatic variations and of variations in human activity such as population growth on shores or in arid areas, which increase or decrease climate vulnerability. Also, the term anthropogenic forcing refers to the influence exerted on a habitat or chemical environment by humans, as opposed to a natural process. Temperature changes. This article breaks down some of the impacts of climate change according to different levels of future global warming. This way of describing impacts has, for instance, been used in the IPCC assessment reports on climate change. The instrumental temperature record shows global warming of around 0.6 degrees Celsius during the 20th century. SRES emissions scenarios. The future level of global warming is uncertain, but a wide range of estimates have been made. The IPCC's SRES scenarios have been frequently used to make projections of future climate change. The SRES scenarios are baseline scenarios, which means that they do not take into account any current or future measures to limit GHG emissions. Emissions projections of the SRES scenarios are broadly comparable in range to the baseline emissions scenarios that have been developed by the scientific community. In the IPCC fourth assessment report, changes in future global mean temperature were projected using the 6 SRES marker emissions scenarios. Emissions projections for the 6 SRES marker scenarios are representative of the full set of 40 SRES scenarios. For the lowest emissions SRES marker scenario, the best estimate for global mean temperature is an increase of 1.8 degrees Celsius by the end of the 21st century. This projection is relative to global temperatures at the end of the 20th century. The likely range for the SRES B1 marker scenario is 1.1 to 2.9 degrees Celsius. For the highest emissions SRES marker scenario, the best estimate for global mean temperature increase is 4.0 0 degrees Celsius, with a likely range of 2.4 to 6.4 degrees Celsius. The range in temperature projections partly reflects the choice of emissions scenario and the climate sensitivity. 4 different scenarios make different assumptions of future social and economic development, which in turn affects projections of greenhouse gas emissions. The projected magnitude of warming by 2100 is closely related to the level of cumulative emissions over the 21st century. The higher the cumulative emissions over this time period, the greater the level of warming is projected to occur. Reflects uncertainty in the response of the climate system to past and future GHG emissions, which is measured by the climate sensitivity. Higher estimates of climate sensitivity lead to greater projected warming, while lower estimates of climate sensitivity lead to less projected warming. Over the next several millennia, projections suggest that global warming could be irreversible. Even if emissions were drastically reduced, global temperatures would remain close to the highest level for at least 1,000 years. Projected warming in context. Scientists have used various proxy data to assess past changes in Earth's climate. Sources of proxy data include historical records, tree rings, corals, fossil pollen, ice cores, and ocean and lake sediments. Analysis of these data suggests that recent warming is unusual in the past 400 years, possibly longer. By the end of the 21st century, temperatures may increase to a level not experienced since the mid-Pliocene, around 3 million years ago. At the time, models suggest that mean global temperatures were about 2 to 3 degrees Celsius warmer than pre-industrial temperature. Even a 2 degrees Celsius rise above the pre-industrial level would be outside the range of temperatures experienced by human civilization. Physical impacts. A broad range of evidence shows that the climate system has warmed. Evidence of global warming is shown in the graphs opposite. Some of the graphs show a positive trend, e.g., increasing temperature over land and the ocean and sea level rise. Other graphs show a negative trend, e.g., decreased snow cover in the northern hemisphere and declining Arctic sea ice extent. Evidence of warming is also apparent in living systems. Human activities have contributed to a number of the observed changes in climate. This contribution has principally been through the burning of fossil fuels, which has led to an increase in the concentration of GHGs in the atmosphere. Another human influence on the climate are sulfur dioxide emissions, which are a precursor to the formation of sulfate aerosols in the atmosphere. Human-induced warming could lead to large-scale, irreversible, and/or abrupt changes in physical systems. An example of this is the melting of ice sheets, which contributes to sea level rise. The probability of warming having unforeseen consequences increases with the rate, magnitude, and duration of climate change. Effects on weather. Observations show that there have been changes in weather. As climate changes, the probabilities of certain types of weather events are affected. Changes have been observed in the amount, intensity, frequency, and type of precipitation. Widespread increases in heavy precipitation have occurred, even in places where total rain amounts have decreased. With medium confidence, IPCC concluded that human influences had contributed to an increase in heavy precipitation events at the global scale. Projections of future changes in precipitation show overall increases in the global average, but with substantial shifts in where and how precipitation falls. Projections suggest a reduction in rainfall in the subtropics, and an increase in precipitation in subpolar latitudes and some equatorial regions. In other words, regions which are dry at present will in general become even drier, while regions that are currently currently wet will in general become even wetter. This projection does not apply to every locale, and in some cases can be modified by local conditions. Extreme weather over most land areas. Since the 1950s, it is very likely that there have been fewer warmer cold days and nights. Hot days and nights have also very likely become warmer or more frequent. Human activities have very likely contributed to these trends. There may have been changes in other climate extremes, but these changes are more difficult to identify. Projections suggest changes in the frequency and intensity of some extreme weather events. Confidence in projections varies over time. Near-term projections. Some changes will probably be evident in the near term, while other near-term changes are more uncertain. Long-term projections. Future climate change will be associated with more very hot days and fewer very cold days. The frequency, length and intensity of heat waves will very likely increase over most land areas. Higher growth in anthropogenic GHG emissions will be associated with larger increases in the frequency and severity of temperature extremes. Assuming high growth in GHG emissions, presently dry regions may be affected by an increase in the risk of drought and reductions in soil moisture. Over most of the mid-latitude land masses and wet tropical regions, extreme precipitation events will very likely become more intense and frequent. Tropical cyclones. At the global scale, the frequency of tropical cyclones will probably decrease or be unchanged. Global mean tropical cyclone maximum wind speed and precipitation rates will likely increase. Changes in tropical cyclones will probably vary by region, but these variations are uncertain. Effects of climate extremes. The impacts of extreme events on the environment and human society will vary. Some impacts will be beneficial, e.g., fewer cold extremes will probably lead to fewer cold deaths. Overall, however, impacts will probably be mostly negative. Cryosphere. The cryosphere is made up of areas of the Earth which are covered by snow or ice. Observed changes in the cryosphere include declines in Arctic sea ice extent, the widespread retreat of alpine glaciers, and reduced snow cover in the northern hemisphere. Solomon et al. assessed the potential impacts of climate change on summertime Arctic sea ice extent, assuming high growth in greenhouse gas emissions. Some models projected that Arctic sea ice in the summer could largely disappear by the end of the 21st century. More recent projections suggest that the Arctic summers could be ice-free as early as 2025 to 2030. During the 21st century, glaciers and snow cover are projected to continue the widespread retreat. In the western mountains of North America, increasing temperatures and changes in precipitation are projected to lead to reduced snowpack. Snowpack is the seasonal accumulation of slow-melting snow. The melting of the Greenland and West Antarctic ice sheets could contribute to sea level rise, especially over long time scales. Changes in the cryosphere are projected to have social impacts. For example, in some regions, glacier retreat could increase the risk of reductions in seasonal water availability. Barnett et al. estimated that more than 1/6 of the world's population rely on glaciers and snowpack for the water supply. Oceans. The role of the oceans in global warming is complex. The oceans serve as a sink for carbon dioxide, taking up much that would otherwise remain in the atmosphere, but increased levels of CO2 have led to ocean acidification. Furthermore, as the temperature of the oceans increases, they become less able to absorb excess CO2. The ocean have also acted as a sink in absorbing extra heat from the atmosphere. The increase in ocean heat content is much larger than any other store of energy in the Earth's heat balance over the two periods 1961 to 2003 and 1993 to 2003. and accounts for more than 90% of the possible increase in heat content of the Earth system during these periods. Global warming is projected to have a number of effects on the oceans. Ongoing effects include rising sea levels due to thermal expansion and melting of glaciers and ice sheets, and warming of the ocean surface, leading to increased temperature stratification. Other possible effects include large-scale changes in ocean circulation, acidification. About one-third of the carbon dioxide emitted by human activity has already been taken up by the oceans. As carbon dioxide dissolves in seawater, carbonic acid is formed, which has the effect of acidifying the ocean, measured as a change in pH. The uptake of human carbon emissions since the year 1750 has led to an average decrease in pH of 0.1 units. Projections using the SRES emissions scenarios suggest a further reduction in average global surface ocean pH of between 0.14 and 0.35 units over the 21st century. The effects of ocean acidification on the marine biosphere have yet to be documented. Laboratory experiments suggest beneficial effects for a few species, with potentially highly detrimental effects for a substantial number of species. With medium confidence, Fischler et al. Projected that future ocean acidification and climate change would impair a wide range of planktonic and shallow benthic marine organisms that use aragonite to make the shells as skeletons, such as corals and marine snails, with significant impacts particularly in the Southern Ocean. Oxygen depletion. The amount of oxygen dissolved in the oceans may decline, with adverse consequences for ocean life. Sea level rise. There is strong evidence that global sea level rose gradually over the 20th century. With high confidence, Bindoff et al. Concluded that between the mid-19th and mid-20th centuries, the rate of sea level rise increased. Authors of the IPCC Fourth Assessment Synthesis Report reported that between the years 1961 and 2003, global average sea level rose at an average rate of 1.8 mm per year, with a range of 1.3 to 2.3 mm year. Between 1993 and 2003, the rate increased above the previous period to 3.1 mm year. Authors of IPCC were uncertain whether the increase in rate from 1993 to 2003 was due to natural variations in sea level over the time period, or whether it reflected an increase in the underlying long-term trend. There are two main factors that have contributed to observed sea level rise. The first is thermal expansion. As ocean water warms, it expands. The second is from the contribution of land-based ice due to increased melting. The major store of water on land is found in glaciers and ice sheets. Anthropogenic forces very likely contributed to sea level rise during the latter half of the 20th century. There is a widespread consensus that substantial long-term sea level rise will continue for centuries to come. In the fourth assessment report is the IPCC projected sea level rise to the end of the 21st century using the SRES emissions scenarios. Across the 6 SRES marker scenarios, sea level was projected to rise by 18 to 59 centimeters, relative to sea level at the end of the 20th century. Thermal expansion is the largest component in these projections, contributing 70 to 75% of the central estimate for all scenarios. Due to a lack of scientific understanding, this sea level level rise estimate does not include all of the possible contributions of ice sheets. An assessment of the scientific literature on climate change was published in 2010 by the U.S. National Research Council. NRC described the projections in AR4 as conservative and summarized the results of more recent studies. Cited studies suggested a great deal of uncertainty in projections. A range of projections suggested possible sea level rise by the end of the 21st century of between 0.56 and 2 meters, relative to sea levels at the end of the 20th century. Ocean temperature rise from 1961 to 2003. The global ocean temperature has risen by 0.10 degrees Celsius from the surface to a depth of 700 meters. There is variability both year to year and over longer time scales, with global ocean heat content observations showing high rates of warming for 1991 to 2003, but some cooling from 2003 to 2007. The temperature of the Antarctic Southern Ocean rose by 0.17 degrees Celsius between the 1950s and the 1980s, nearly twice the rate for the world's oceans as a whole. As well as having effects on ecosystems, warming reduces the ocean's ability to absorb CO2. It is likely that anthropogenic forcing contributed to the general warming observed in the upper several hundred meters of the ocean during the latter half of the 20th century. Regional effects of global warming vary in nature. Some are the result of a generalized global change, such as rising temperature, resulting in local effects, such as melting ice. In other cases, a change may be related to a change in a particular ocean current or weather system. In such cases, the regional effect may be disproportionate and will not necessarily follow the global trend. There are three major ways in which global warming will make changes to regional climate: melting or forming ice, changing the hydrological cycle, and changing currents in the oceans and air flows in the atmosphere. The coast can also be considered a region, and will suffer severe impacts from sea level rise. Observed impacts. With very high confidence, Rosenzweig et al. Concluded that physical and biological systems on all continents and in most oceans had been affected by recent climate changes, particularly regional temperature increases. Impacts include earlier leafing of trees and plants over many regions, movements of species to higher latitudes and altitudes in the northern hemisphere, changes in bird migrations in Europe, North America and Australia, and shifting of the ocean's plankton and fish from cold to warm adapted communities. The human influence on the climate can be seen in the geographical pattern of observed warming, with greater temperature increases over land and in polar regions rather than over the oceans. Using models, it is possible to identify the human signal of global warming over both land and ocean areas. Projected impacts. Projections of future climate changes at the regional scale do not hold as high a level of scientific confidence as projections made at the global scale. It is, however, expected that future warming will follow a similar geographical pattern to that seen already, with greatest warming over land and high northern latitudes, and least over the Southern Ocean and parts of the North Atlantic Ocean. Nearly all land areas will very likely warm more than the global average. The Arctic, Africa, small islands and Asian megadeltas are regions that are likely to be especially affected by climate change. Low-latitude, less developed areas are at most risk of experiencing negative impacts due to climate change. Developed countries are also vulnerable to climate change. For example, developed countries will be negatively affected by increases in the severity and frequency of some extreme weather events, such as heat waves. In all regions, some people can be particularly at risk from climate change, such as the poor, young children and the elderly.